Okay, I think we can start. It's 4 p.m. So, dear colleagues, I'd like to introduce you our great friend and colleague, Professor Juan Domingo Baena from the Department of Physics in National University in Colombia. So his talk is devoted to left-handed metamaterials meshed to the free space. And so, dear Juan, please start.
Oh, thank you very much. So, well, you have already read my title, but let me repeat again. It is about left-handed metamaterials matched to free space. This work is being done by one of my students, Ana Cristina Escobar, and she is a master science student at this moment. And well, let me start. This is the outline of the talk, some introduction. In the blue region of this slide, you can see that I will talk something about left-handed medium, impedance matching in left-handed medium, and I will introduce the Coco resonator or Coco particle as a Huygens source that I'm going to use in order to make a left-handed medium matched to the free space. In the green region of the outline, well, I will tell some words about the dispersion relation of the Coco metamaterial. I mean, a metamaterial made with the Coco particle. I will show the S parameters of that metamaterial, and I will try to demonstrate backward propagation through a GIF animation. In the red part of the outline, you can read multimodal transfer matrix method. We have used this method to retrieve the material parameters. And finally, the conclusions. Then let's start. Well, some small brief words about V.G.Veselago. You know that he proposed media with simultaneously negative permittivity and permeability, or you know about right-handed medium with forward propagation, while left-handed medium shows backward propagation. In fact, you can demonstrate negative refraction for the second type of medium, while for right-handed medium, which is the most common type of medium, you have positive refraction. This is very well known. And the first time this kind of left-handed medium was demonstrated as an artificial structure, it was in 2000. Probably you know this experiment in David Smith group with the split-ring resonator and metallic wires. Metallic wires provide the negative permittivity, while split-ring resonator is providing the negative permeability. When you use only SRRs, you can get a stop band, while by using SRR and the metallic wires at the same time, you can get a passband. Unfortunately, this passband is not reaching 0 dB. I mean, it is not reaching total transmission, as you can see in the figure on the right side. The transmitted power is something about -30 dBm. It is very low transmission at the top of the I mean, at the biggest transmission you are getting -30 dBm. It's very low. It could be due to the losses in the material, or maybe it can be due to impedance mismatch. Actually, they both are the reason of this low transmission in the passband. In fact, we were trying to repeat this experiment numerically. Here I'm showing you the transmission coefficient S21 parameter for a structure made of perfect electric conductor. In the inset, you can see the split-ring resonators and the wires. They all are made of perfect electric conductor. You have 10 unit cells in depth. You have also periodic boundary conditions around along the longest direction of this tetrahedral. You have the propagation direction. Okay, I mean that the wave is propagating along the longest side of this parallelepiped. Okay. Well, we get this kind of cone curve with many peaks. In fact, since we have 10 unit cells in depth, we can observe 10 peaks in the cone. You can count the number of peaks. It is about 10, maybe 9, exactly 9. It seems one of the 10 peaks is missed. But anyway, this is the type of curve that you can observe in a Fabry-Perot resonator. It is because there is some jump in the impedance between the free space and the metamaterial. So you have two strong reflections at the beginning of the metamaterial and at the end of the metamaterial. Consequently, you can observe a kind of Fabry-Perot resonator. Well, some time ago, we were very involved in research of left-handed metamaterials. It is, well, I would like to say some references to my previous work between 2004 and 2009. For instance, in the three first resonant references, are devoted to focusing, super resolution, or subdiffraction imaging. They are very similar terms. Well, we found that super resolution is very limited by strong dispersion and strong dissipation, and basically you can get super resolution only for very thin metamaterial slabs because of losses, dispersion, dissipation, etc. In the references in green refers to how to make isotropic metamaterials. This is another difficult point. And the two references in blue are related with homogenization theory. We found, as other people, that non-local effects in metamaterials are important, and it could be also a difficulty if you want to get super resolution. Well, it is only about all references. I would like to show also this old work. It is done in Stephen Kammer's lab. In this paper, they were trying to make a metamaterial with the same wave impedance as the free space, at least for a range of frequencies. The idea in this work, you can read the title, Negative Index Material Composed of Electric and Magnetic Resonators. They thought that maybe by using ELC and SRR, ELC means electric LC resonator, and the split ring resonator is giving the magnetic response. Well, maybe using these two types of resonators, they can fix the geometry in order to get the same permeability as the permittivity. I mean, they were trying to get the same curves for mu and epsilon. Mu coming from the SRR and epsilon coming from the ELC resonator. It seems that they got that aim in numerical simulations, but as you can see in this figure, they had to control many parameters in the geometry. And well, it is quite difficult to get the experimental sample exactly with the same geometrical parameters as they numerically simulated. So I think that they can fix the geometries in order to have impedance, the free impedance, the free space impedance equal to the impedance of the metamaterial. I think they can get that in numerical simulation, but it is very difficult to get in the experimental sample, because it's very difficult to make exactly the same as you were simulating. Even you cannot be sure that the numerical simulation is exact. So it is quite difficult. In fact, I had the opportunity to stay with these people during the same years they were making the experiment, and I could see that the transmission was not good. Well, you can observe the passband related with the left-handed band, but there is some strong reflection for this metamaterial. Anyway, you can see the results for numerical simulation. It is very nice. They get a band between, I would say, 11 and 12 gigahertz approximately, where they have theta close to 1 or near 1. But in the experiment, they are retrieving only the refractive index, while this method by Shen and others, published in 2005, can allow them to get n and theta. But it is curious that they are showing only experimental results for n, the refractive index, but not for theta, the impedance. It is because the experimental result was not very good. It is my personal opinion, okay? Then why it was not very good? Because it is very difficult to make the geometrical parameters that you really want. And the structure is very sensitive to small deviations in the fabrication. So some years ago, a couple of years ago, we were investigating about this resonator. We like to call this resonator channel or Coco channel, or maybe Coco, which is why Coco? Because it is resembling the trademark logo of Coco Channel Company, okay? But the resonator has two differences with the Coco Channel logo. The first one is that it is made in two parallel surfaces. You can see the top view here. We have metal over two parallel surfaces. And the second difference is that we need to add some ledges to the particle in order to get the same electric response as magnetic response. They should have the same intensity. I mean, in other words, the electric dipole and magnetic dipole close to the resonant frequency should have the same intensity. So we need to play with the length L of the ledge in order to get that. Well, you can see here some circuit equations in the box. You can read theta 11 is the self-impedance of the ring number 1. Theta 22 will be the self-impedance of the ring number 2. I1, I2 are the currents of the two rings. Theta 12, theta 21 is the mutual impedance, because in principle there could be some coupling between the two parts of the resonator. On the right side of the circuit equations, you can read the electromotive force that can be due to the incident magnetic field, but also to the incident electric field. It's important to see that the sign for the magnetic part of the electromotive force is the same for both equations, but the sign in the electric part is opposite. It is because the electric field, the incident electric field, has to excite the capacitors made with the ledges of the two rings. For one capacitor, the electromotive force, well, having the same direction of the electric field on both capacitors, for one capacitor, the electric field is in the same direction as the current of the ring. For the other capacitor, it is in the opposite direction. So sometimes the electromotive force due to the electric field is against, other times it is in the same sense as the current. Well, it is worth to note that when you want to get the same electric dipole and magnetic dipole, these two rings should be uncoupled. So you can see here that we are looking for the situation in which theta 1,2 and theta 2,1 are equal 0. Because in that way, P and M can be very similar. Not exactly equal because they have a different dependence on omega. You can see how magnetic dipole is proportional to omega, while electric dipole is proportional to 1 over omega. But if we concentrate ourselves in the resonant frequencies, so omega is basically one number. Well, there is some bandwidth, but this bandwidth is relatively small. So we can fix other numbers like D or A, distance D or area A, in order to have a very similar function for P and M. The strongest dependence on the frequency is not omega, but the impedance. The impedance has some resonance. So if I remove theta 1,2, I can see now in the denominator theta 1,1 for P and M. So the frequency dependence of electric dipole and magnetic dipole is very similar. This is necessary if I want to make Huygens scatterers. Well, this is only to show it is difficult to explain this type of resonance because it is a kind of hybridization between the magnetic and electric resonance, but I will try, okay? In the figure on the left side, you see the current and charge for each part of the resonator. There are two metallic parts. I1, Q1 are related to the ring number 1, I2 and Q2 to the ring number 2. And you can see here the time evolution of current and charge. Basically, the current of the ring number 1 is time delayed respect to the current of ring number 2. The time delay is pi over 2. It means some 90-degree phase delay or something like that, okay? The same, you can observe the same for charge. Q1 and Q2 are the charge saved in the capacitors. Store in the capacitor. And then you can see how there is some time delay between the two curves in blue. Oh, well, the figures in the middle is showing the current. You can see how this resonant mode is even half of the time, but odd half of the time also. So it is not an even mode or odd mode. It is even and odd at the same time. It is connected with the 90-degree phase shift between the current of the ring number 1 and the ring number 2. Sometimes they have the current in the same sense. Other times the currents are opposite. This is well documented in the Physical Review Applied. You can read the reference right below. And well, if you are interested in understanding this strange way of resonating, you can read the paper. If you don't think it is a Huygens source, well, this slide is more clear, I think. We have a method, a general method to retrieve the electromagnetic polarizability developed by one of my partners, Javier Leonardo Araque, and myself. We were telling about this method in metamaterials in 2013. And we can get the polarizability by launching 6 different plane waves over the scatterer. You can see here plane wave number 1, number 2 to number 6. And by using the method of moment, we can get the currents over the metal. From the currents, we can get electric dipole and magnetic dipole by doing some integrals. And finally, we can retrieve the polarizability tensor. You can see here how the electric part of polarizability is very similar to the magnetic part. There is a very small response in the electric magnetic part. It is very small because of the inversion symmetry in the particle. In fact, when the electrical side of the particle tends to 0, it should be rigorously 0. There shouldn't be any magnetoelectric coupling for this particle. But let's come back to the electric and magnetic parts. Well, in the electric part, you see these blue lines. The solid blue line is the real part of the electric polarizability, while the dashed line in blue is the imaginary part. And they are very similar to the green curves for the alpha MM, which belongs to the theta component. In fact, it is quite clear from the figure that this particle should show some magnetic response when magnetic field is directed along the theta axis. On the other hand, it can also respond when the electric field is directed along the y-axis in the vertical direction. And well, basically we got the same electric and magnetic response, the same level of response. This is another way to demonstrate that it is a kind of hybridization of the resonant modes. If you change slightly the parameter S, you can see in the figure parameter S is the lateral shift between the 2 rings. You can get 2 separated resonances. One of them could be electric and the other one magnetic. In other words, even and odd modes. But if you move to the exact value of S equal to 2.53, then you can get only one single resonance. That is the generation of the 2 previous ones. In the figure, you can see the red curve belongs to the case of S equal to 0.53 millimeters. In that case, we can see only one single resonance, which is at the same time electric and magnetic. In fact, in the inset, you can see also the radiation diagram for that case at the resonant frequency, which is about 8.7 gigahertz for this specific geometry. Well, we are very happy because these Coco have given us 2 recent publications. The first one was in 2018 with, this was a collaboration with Stanislav Glybovski and Andrei Zhirihin. And you can read the title. It was about broadband Huygens metasurface based on the hybrid resonance that I was telling you. Well, I put here a picture of this is the sketch of the measurement. We were measuring for different incident angles, and we were able to demonstrate that this structure is quite transparent. You can see on the right side the transmission coefficient. The magnitude of transmission coefficient is near 1 in a wide range of frequencies, while there is some phase jump when the wave is crossing the structure. So it could be used as a kind of polarization converter, or maybe phase delay. More recently, just 1 month ago, I think, we have published this second paper on the optimal angular stability of reflectionless metasurface absorbers. Well, the idea was to use the same Coco to absorb all the power that is being on the metasurface. It is basically the same structure, but now the substrate, the dielectric substrate, is very lossy, and we found a way to absorb all the power at one single frequency, while the reflection in a very broad range of frequency is negligible, basically zero reflection. And besides, we found a very good angular stability of the absorption at the resonant frequency. As you can see in the second figure, you see that the absorption is very high for angles, incident angles, close to near 60 degrees. In fact, we have a theory developed some years ago where we found the theoretical optimal angular stability, and this structure is reaching values very close to that theoretical optimal. So, well, for now, the Coco was useful to make phase shifter, absorber, and in this talk, I want to use this Coco geometry to make a left-handed medium matched to free space. The idea is that it is a Huygens source, so the electric and magnetic response have the same intensity. So it could be helpful in order to get the same permittivity as permeability. And finally, impedance close to the free space impedance. Well, okay, now introduction is gone. It is the real start of the talk. Let me show you the dispersion relation of the Coco metamaterial. This, you can see here the unit cell of the metamaterial. It is inside a parallelepiped made with periodic boundary conditions. The metal is perfect electric conductor. You can read the geometrical dimensions. Maybe just to give you an idea, the radius of the particle is 4 millimeters. The radius of one ring is 4 millimeters. And the unit cell size is 1 centimeter, just to give an idea. By using the CST eigenmode solver, we can get the dispersion relation. You can see that dispersion relation on the right side. In fact, there are some right-handed bands, and you can see also some left-handed band. The left-handed band is going from approximately 3.4 gigahertz to 3.6 gigahertz. The bandwidth is not big. You know, this is a kind of well, this is based in a resonance, so it cannot be a broad band. But it is not too sharp. It is 0.2 gigahertz, while the center of the central frequency is about 3.5 gigahertz. It is less than 10% in the bandwidth, but not very far from 10. Well, you can see also some stop bands, very sharp stop bands, which are depicted with a gray shadow. They are shadow in gray. Well, let me analyze carefully this question of the variation of the S parameter. You remember that if I move the lateral shift between the two rings, you can see the lateral shift S equal 2 millimeter, 4 millimeter, 5.6 millimeter. It is the optimal one. Well, when you move the S parameter value, there is some point at which the hybridization of the electric and magnetic resonance is perfect, and then you get the same, almost the same polarizability for magnetic and electric parts. Well, in the figure you can see how what is the direction of the electric field, what's the direction of the propagation. It is propagating along the horizontal direction, and electric field is vertical. For the first figure, we have the magnetic resonance at 2.7 gigahertz, while the electric resonance is about 4.5 gigahertz, more or less. They are well separated, so we cannot see any left-handed band. But if we move to S equal 4 millimeters, they are also well separated, but much closer. With the exact value of S equal 5.6 millimeter, we get the left-handed medium band, which is clear because of the slope of the dispersion relation, which is negative. You can see also some straight line, which I'm trying to point with the hand. This straight line corresponds to the free space cone, or maybe the light cone in free space. Okay. This is because we are trying also electric field orthogonal to the metal. In this figure, I'm showing you electric field along the vertical direction, but in the ITMO solver, we are trying all possibilities at the same time. Also, the electric field perpendicular to metal, going out from the screen. For that case, the electric field is not interacting with the metal. It is satisfying directly the boundary conditions of perfect electric conductor, so there is no response. And then we can get the dispersion relation for free space, which is this straight line. Okay, coming back to the polarization that for which we get the left-handed medium, which is the vertical polarization. You can see in the inset of this figure, the electric field is vertical, magnetic field is perpendicular to the Cocos. I'm sorry that Coco particles are very small in this figure, but I hope you can understand the figure. The propagation of the wave is going through the longest direction of the bounding box. All boundaries around are periodic boundaries, except for the faces orthogonal to the theta or k direction, where we have block-floquet ports. By using the CST frequency domain solver and the block-floquet ports, we can get this transmittance and reflectance. It is very important to note that it is transmittance, but not the magnitude of the S21. It is magnitude of S21 to the second power. The same for reflectance. I mean, it is a power, but not S parameter. Transmitted power and reflected power. In this figure, you can see the left-handed medium just in the middle, about around 3.5 gigahertz. In the inset, the figure is more clear for us because I'm showing only from 3.2 to 3.8 gigahertz, just to increase the left-handed medium part of the figure. And you can see how the effect of the Fabry-Perot is not very important. This is because we are getting a good free impedance, a good matching with the impedance of free space. So the comp is not very important. You can see how the peaks are not important. The curve is very flat in between 3.4 and 3. I would say almost 3.6, okay? 3.4 to 3.6. The curve is very flat. There is some stop band below 3.4 and very near 3.6 gigahertz. Those stop bands are due to the fact that you cannot get the exact same curve for permittivity and permeability. So one of them, epsilon or mu, is negative, while the other one is positive in a very sharp region of frequencies. At the center of the left-handed medium band, we think we are getting the same epsilon and mu, but the shape of the curves are not exactly the same. They are very similar, but maybe you remember the frequency dependence was not exactly the same. So you cannot get the exact matching between epsilon and mu. As a consequence, you can get some stop bands around the left-handed medium band. In fact, those stop bands were already observed in the dispersion relation. Well, let me stop here and show you some animation. Okay, it is here. Well, I hope you can see how the wave is impinging from theta minimum. You have some wave coming to the structure from the up side of the bounding box. It is impinging on the metastructure. There is no reflection. Well, you can observe also the wave coming out from the metastructure in the downside of the figure. And inside the metastructure, maybe you are able to see that the phase is traveling in opposite direction to the energy. I would like to know if the movie is working or not.
Yeah, it's working.
So can you see clearly how the wave is traveling in the wrong direction?
Yes.
Okay. Then let me go back to the presentation. Okay. So this is the static image of the same movie. Well, this image was obtained, this movie was obtained for frequency equal to 3.4 gigahertz. It is inside the left-handed band. Well, the wave vector and the pointing vector are parallel outside in the free space, while they are anti-parallel inside the metastructure. Okay, but maybe you are not fully convinced that it is a left-handed medium very well matched with the free space. So I'm going to use the multimodal transfer matrix method in order to get permittivity and permeability. and show the results. Well, let me explain the basics of this multimodal transfer matrix method. Imagine you have some bounding box with periodic boundaries around and some block floquet ports, number 1 and number 2. In block floquet ports, you can use transfer electric or transfer magnetic modes. There are infinite set of modes. Well, some of those modes are propagative, but others are evanescent. It depends on the lateral dimension of the boundary box. Well, normally you have transfer electric 0, 0 and transfer magnetic 0, 0 are the only propagative modes. But if you increase the periodicity of your structure, maybe you have more propagative modes for this structure. Well, the bounding box can be replaced by some scattering parameters matrix. In the figure below, you see the same structure, but now it is a kind of periodic, well, actually it is a periodic structure for the metamaterial, but not for the numerical simulation. We are going to use CST frequency domain solver in order to get the S parameters, but not only S parameters for the propagative modes, but many modes. So these scattering parameters are matrix. So you can see the sketch on the right side of the slide. You see the sketch of the method. First, by using some numerical simulator, we can get multimodal S parameter matrix. With that, we could get the multimodal ABCD matrix. Now A, B, C, and D are matrix, but not numbers. By solving the eigenvalue problem, we can get the dispersion relation for this structure. I'm going to show how to get also the impedance. Once I have the dispersion relation, which is mainly the refractive index, and at the same time I have the impedance, then I can get the effective permittivity and effective permeability of the medium. This is the idea. And now let me explain. Well, imagine that I have already obtained the S parameters. How can I traduce from S parameters to ABCD matrix? This is only a problem of algebra. But I would like to point that these formulas are already used in a paper by Francisco Mesa, who is a collaborator of us working in University of Seville. They were publishing recently in 2020 this paper, nice paper, with the multimodal transfer matrix method, just to get the dispersion relation. But in this presentation, I want to show you that we can get more than the dispersion relation. We can get the constitutive parameters of the metamaterial. Well, you can find very similar formulas to this in the Pothar's book on microwave engineering. But those formulas are devoted to a system for which A, B, C, and D are complex numbers, but not matrix. I mean, only for the propagative modes, but not for the multimodal case. Well, this is only a problem of algebra. I was working with the algebra, and I got the formulas which are very similar to the ones that you can find in Pothar's book, but they are not equal because of the matrix nature of this formula. Anyway, you can see in those formulas theta PM. It is PM means port mode. They are the impedances in the port mode. So they could be transfer electric modes or transfer magnetic modes. You have these two formulas for the impedance of each mode. Please note that for the case 0, 0, the impedance becomes the same for transfer electric and transfer magnetic. And actually they are the same as the free space impedance. For the case I equal J equal 0. We are going to use those modes, TE00 and TM00, but also we are going to use higher order modes. So just for the case of the lowest order modes, 0, 0, the impedance at the port is equal to the free space impedance. For other modes, you have to change and use these formulas. Well, once you get the ABCD matrix, please remember that A, B, C, and D are box. They are also matrix. Well, you can think about some block theorem. Probably you know the block theorem for periodic structures. So in this formula here, well, what we have here? Here in the first column, we have voltage and current at port number 1. In the last column, we have the same voltage and current, but for the second port. You can relate those columns by using the block theorem. The voltage at port number 1 and voltage at port number 2 are connected by some exponential because of the Bloch's theorem. So we can read the last equation, the last equality, and now we see here an eigenvalue problem. Okay. The last part of the formula is obtained by using the Bloch's theorem, and it is connected with the first part of the formula. You see here voltage and current at theta sub n minus 1, and after at theta sub n. They are connected, but they are also connected through the ABCD matrix, which is the transfer matrix for this problem. So by solving the eigenvalue equation, we could get K, the wave vector. The wave vector K has some real part, which is called beta, it is the propagation constant, and imaginary part, alpha, which is the attenuation constant. Okay, but well, it is not the only thing that we can get. We can get the dispersion relation by solving eigenvalues, but we have also eigenvectors. From eigenvectors, we could get the impedance, and this is the formula at the bottom. Imagine you can get, you want to get impedance for Y polarized waves. That impedance will be the ratio between the average electric field and average magnetic field. Well, for Y polarization, electric field is along Y. For that reason, you can read here EY, and magnetic field is along the X direction. So average of HX. Higher order modes corresponds with fields that has some periodic variation inside the unit cell. In such a case, the average is equal 0. So higher order modes are not going to contribute to the average of electric, neither to the average of magnetic field. All that we have here is B1 plus, B1 minus that belongs to the propagative transverse electric 0-0 mode. Actually, the numerical simulation was done with many modes, but we think that higher order modes are not contributing to the average of electric field, so they are not included in this integral. If you read the formula in the denominator, it is the same. We are only considering the currents connected with the TE00 mode. So at the end, the impedance, the wave impedance for the metamaterial that you have will be something like V1 over I1. V1, I1 are the components of eigenvectors, the first component of the eigenvectors, V1 and I1. If you want to get the impedance for X polarized waves, that will be V2 over I2. If we are talking about impedance, we don't need to use any other components, B3, B4. They are not important because they are related with higher order modes. And I told you that the average of the electric field is 0 inside the unit cell. So, okay, it is summarized here. Let's move to this slide. Now this is more clear. The multimodal transfer matrix method can give me eigenvalues. From eigenvalues, I can get the dispersion relation. But if I remember that refractive index is K over omega, I can also get, from the eigenvalues, I can also get the square root of mu epsilon. On the other side, from the eigenvectors, I can get also some important, very important information. It is the impedance. Zeta y will be V1 over I1, zeta x is equal V2 over I2. Actually, for the case of the metamaterial I'm going to study, only theta y is relevant for us, because the Coco particle can be excited just with the Y polarization. So I'm going to use these formulas and the method of multimodal transfer matrix to get permittivity, permeability, dispersion relation, all those things, refractive index. So here in this slide, you can see the dispersion relation. First, we try to use only the propagative modes, the lowest order modes, 0, 0. And we found that it is almost the same as using many modes for the specific case of this structure. Well, in this dispersion relation, you can see in red and blue, you have the dispersion relation obtained with the method. In black, we have the eigenmode solver. But the eigenmode solver of CST can give me only the real part of the wave vector. There is no way to get the imaginary part. With this method, we can get also the imaginary part, which is the blue curve. You can see how the real parts are very similar. Red and black dots are following very similar path. So it is a kind of confirmation that our multimodal transfer matrix method is working, but we cannot compare the imaginary part because the eigenmode solver cannot get that. In this slide, I'm showing relative impedance relative to the free space impedance. So if the structure is well matched to the free space, the relative impedance should be 1 or -1, as in this case. In fact, I would like to say that the sign of the relative impedance inside the left-handed medium can be positive or negative depending on the definition that you use for impedance. Sometimes impedance is defined as just the ratio between EY and HX. In that case, it should be positive in this region. This impedance close to -1 should be close to +1. But sometimes it is defined in terms of the direction or helicity of the medium, and there could be some minus sign, but actually it is not very important. It depends only on the definition. are you considering the direction between E, H, and K? If the vector product between E and H has to point along K, sometimes you use that definition, then the free impedance for right-handed medium should be positive, but for left-handed medium should be negative because the vector product between E and H is just opposite to the wave vector, okay? But depending on the definition, this impedance can be positive or negative. You have to be only coherent with your definition, nothing else. And here I'm showing you the relative impedance again, the real imaginary part, and the index of refraction on the right side. You can see how there is, for instance, you can see here that refractive index can be negative. For instance, you can get at some frequency you have n equal -1. Even you can get also 0. Anyway, this is the relative permittivity and relative permeability. Those figures correspond with the case of only 2 modes in the numerical simulator. We were using TE00 and TM00. But our method is multimodal. So I should increase the number of modes to take advantage of the multimodal method. So let me go to 10 modes. In this figure, we have again the dispersion relation. Actually, I'm showing now from 3 to 4 gigahertz to increase, not to increase, but to make the visualization of the left-handed band easier. So this frequency band is shorter. And well, in this figure, you can see the the eigenmode solver results are painted in red, while the multimodal transfer matrix method is in black or gray. Black for 2 modes, which is the same result as I was showing, and 10 modes. What does it mean? 2 modes is 0, 0. 10 modes include transfer electric and transfer magnetic with 1, 0, 0, 1, -1, 0, etc. We can introduce also 1, 1, but it is in a different group because it is higher than 1, 0. 1, 1 will be more evanescent than 1, 0. Or maybe we can use 2, 0. We are doing all those trials, but anyway, we see for this specific structure that even there is no important difference between 10 modes and 2 modes. So the method has converged with 2 modes, basically. It is a kind of very fast convergence of the multimodal method, transfer matrix method, because the Coco are not too much coupled one to another through higher order modes. They are coupled, but just with the lowest modes. For different structure, the situation can be very different, and we may need many modes to describe exactly the behavior. Anyway, let me show you the attenuation constant. It cannot be obtained with the eigenmode solver in CST or many numerical simulators. It cannot obtain this attenuation constant. Our method can get it. This is the refractive index, real part and imaginary part. This is the impedance, real and imaginary parts. In all these figures, you can see how by using 2 lowest order modes, you get the same as using 10 modes, the 2 propagative and the next 8 evanescent modes. So you get basically the same results. And since you have the refractive index and the impedance, you can get also permittivity and permeability. Here you have the permittivity, real and imaginary parts. Again, the method has converged with very few modes, just 2. Actually 1, because the transfer magnetic 0,0 cannot excite the resonance of the Coco. So with only 1 mode, we will obtain just the same. And here you have the permeability, the real part on the left side, the imaginary part on the right side. Let me remind you that the left-handed band is between 3.4 and 3.6 gigahertz. Well, since our method can allow us to get the attenuation constant, we decided to play with copper. In all the previous results, I was using perfect electric conductor. I told you that the eigenmode solver of CST can allow you to get the dispersion relation for perfect electric conductor. But our method can also can allow us to get the dispersion relation for including metal losses. Well, in this case, we were playing with copper, and now you see the attenuation constant in the left-handed band is not 0. There is some attenuation constant. Well, we are showing here the positive and the negative values. Positive values positive value of the attenuation constant alpha belongs to waves that travel from left to right. The negative values for waves traveling in the opposite direction. And well, here you have the refractive index, real and imaginary parts. Actually, they are almost the same as the dispersion relation, because it is n is equal to is proportional to k. Here you have the impedance. So you can see how between 3.4 and 3.6 gigahertz, we have something very similar to 1. It means the free space impedance. Well, finally, the real part and imaginary part of the permittivity. I'm sorry that I wrote here impedance, but it is permittivity and permeability. Well, then let me conclude. Well, we have introduced a left-handed medium made of Cocos. Well, actually, it is left-handed only within the range between 3.4 and 3.6 gigahertz, approximately. You can read the numbers here, 3.38, 3.59 gigahertz. It is very important that the transmission is almost total. The transmission coefficient is very close to 1. There is no cone with many peaks inside the left-handed band, but it is very flat and close to 1. The multimodal transfer matrix method was used and was extended because our friend Francisco Mesa developed this method only to get the dispersion relation, complex dispersion relation, with including the attenuation constant. But we have extended the method to retrieve the impedance. Once we have the dispersion relation and the impedance, we can retrieve permittivity and permeability. In fact, we have found that permittivity and permeability are very similar They are not the same curve, but they are very similar in a certain range of frequencies within the left-handed band. It is possible, if we take a look on the numbers, not the figures, but the numbers, we can find a specific frequency, which is about 3.5 gigahertz, for which permittivity and permeability are equal -1. But we can also get epsilon mu near zero media. Maybe you know those medias like near zero index metamaterial, they are the same idea, at about 3.6 gigahertz. Because, well, I have said that permittivity and permeability are very close and they are resonant. So at some moment, they both cross the level of zero almost at the same time. So you can get epsilon and mu very close to zero. Actually, when we were trying with copper, we found that epsilon and mu are equal to zero, while the imaginary part is about 0.02. I remember. It means that it is not only that the real part of epsilon and mu are close to zero, but at the same time, when we are using copper, the imaginary part is very low. So what are the next steps? Well, we could stop here because it is only about a method that can allow us to get permittivity and permeability. And for some specific case, we can get epsilon and negative epsilon and negative mu, but it is all stuff. Nobody is already interested in making sub-wavelength focusing or negative refraction. But anyway, we could try to get negative refraction. Or maybe, since we can get near 3.6 gigahertz, epsilon and mu very close to zero, we could try to get total transmission through a waveguide with a kind of bottleneck. You know that there is a paper by Mario Silveriña where they have a waveguide with some kind of very general bottleneck, and the wave can be propagated through that obstacle without any difficulty, because the obstacle is filled with epsilon and mu equal zero. So, well, thank you very much for your attention.
Okay, thank you, Juan, for the interesting talk. So, dear colleagues, do you have any questions to the speaker? So you can ask in the chat or raise a hand. Okay, Stas has a question. Please, Stas.
Yes, thank you so much. Thank you, Juan, for this very instructive talk. I have a question regarding the experimental characterization, a possible experimental characterization of the non-reflective metamaterial based on Coco, what you were speaking about at 3.6 gigahertz. So you were mentioning the effect of the copper losses to the attenuation constant. But what will happen if we print these particles over a dielectric substrate, and in particular a substrate like FR4? Because previously I think I was mentioning to you that it could be too expensive to produce a full 3D metamaterial for this kind of experiment. But now I think that it is in fact would be quite possible if we use FR4. But would it deteriorate the properties, or it is acceptable? How do you think?
I think we cannot use FR4 if we want to measure the transmission coefficient. Maybe for reflection we can use FR4, but not for transmission. In fact, well, Anna is trying to get the results for the gate with substrate. I'm not showing any result with the substrate because the talk was quite long. And I think it is more clear to show perfect electric conductor, and after that the method can be used also when there is some kind of losses. metal losses in this case. So we have only introduced copper to not make it more difficult. But the method can work easily with the dielectric substrate. So Anna is getting many results with some dielectric substrate. But she is playing with a very low loss tangent, but the typical one for microwaves, 10 to minus 3. It can work, but anyway, the metamaterial has to be short. The slab has to be thin, relatively thin. Otherwise, the transmission is very low. But okay, you have two reasons for very low transmission. The impedance mismatch with the free space. We are fighting against that reason, but you have also the dissipation. Dissipation of copper is already a problem because you have already seen in this figure how maybe here, you have here the attenuation constant due only to copper. Well, it is much less than in between 3.4 and 3.6. It is much less than in the first stop band. But, well, not much less. It is 1/3. So the attenuation constant in the first stop band is about 0.2, a little bit more than 0.2. Inside the left-handed band, it is 0.3, maybe, no, sorry, not 0.3, but 0. For sure, less than 0.1. I will say 0.7, maybe, yes, 0.7. And, well, I don't know. I have some, I will say the dielectric substrate should be well, it is important, very low losses. It's important to use very low losses in the dielectric substrate because just the copper is a problem, I think. It depends on the thickness of the sample. It could be thinner because we were trying a relatively thick slab with 10 unit cells, but we can make it shorter, probably.
Okay, but what's the difference between the freestanding sample and the waveguide insertion? In both cases, you will have such losses if you have a substrate, right?
Yes. Yes.
Okay. No, I'm wondering just how bad it is for the experimental results. Despite this loss, you can also retrieve this, and at least you can characterize the same thing as you show here. Of course, the paper is not about how to avoid losses at all in the metamaterials.
Oh, okay. Let me think. If you want to get this from the experimental results, well, we could work with the propagative modes. With only 2 modes, we could get the dispersion relation and the impedance, but we cannot work in the experiment with higher order mode, isn't it?
No, you mean excitation? Or excitation is only with the 0 order modes, of course.
I agree with the 0, 0. It means that but you can see in this figure that we have the group number 1 and group number 2. Group number 1 is using only 2 modes. They are 0, 0. They are the only ones that you can make in the experiment, but you cannot use the higher order modes because they are evanescent. So, but for this specific geometry, the propagative modes are enough. So we could try to get the same result by just measuring 1 unit cell. You have to put only 1 unit cell to get this.
Okay.
but you should be very expert with the TRL calibration method, because you need to put the reference planes yet at the beginning of the unit cell and at the end.
Yeah, of course, it's something one cannot avoid.
Mm-hmm.
to be an expert in this. Otherwise, no measurements are possible.
Yes.
Okay, thank you.
Not at all. But I was thinking that, well, anyways, is there any other question?
So are there any other questions, guys? So actually, I have another question, but maybe a comment about the previous question. So you want to make 3D metamaterial, but what if you make just one layer of these Coco metamaterials and put it inside the parallel plate waveguide? In some case, when you can make this metallic boundaries like a periodic boundary condition, and this can like make maybe much easier to experimentally realize, and possibly you can purchase Arlon or so on substrate with low losses, which is a problem because of the huge amount of money to purchase it. So maybe it can help.
Yes, I agree. In fact, I have two possibilities in mind by using parallel plate waveguides. One of them is, imagine a parallel plate waveguide with a jump. Just the parallel plate waveguide without any metastructure inside. You have the parallel plates and some jump. The height on one side is small, the height on the second side of the parallel plate waveguide is higher, okay? So you have some jump, something like this, okay? It has to reflect the wave because there is some variation of the shape of the waveguide, so it will reflect some part of the energy. But now you can fill the structure with these Cocos and play around the frequency where you think epsilon and mu are near zero. And probably the waveguide is going to transmit much better for that frequency. So imagine, I don't know if you understood the point, the jump in the parallel plate waveguide.
Yeah.
The jump. Okay. And you can feel, well, I could try to draw here. I don't have any pen right now, but I could draw with a touchpad.
Yeah, but it looks like it is coming too close to classical impedance matching techniques. So if you have some waveguide which has cutoff, but you can simply connect two parts of this waveguide by coaxial cable and use two small probes on both sides to connect them.
Yes. Imagine we have here the Coco. It is the first parallel plate with a small distance between the plates. And we can use here a few Cocos working with epsilon and mu equal 0. And some Cocos in the taller waveguide. This is one possibility I'm thinking. Well, you can imagine. I could put many more Cocos, but it is difficult. Well, at least one more. I'm very sorry, but I forgot to carry with me the mouse, so I'm using directly the touchpad. Well, maybe well, and we could have the reference planes at some distance from the Cocos, something like this. It will be the reference plane. in the, well, maybe at the frequency at which epsilon and mu is equal 0, the transmission should be much better. If you remove the Cocos, there should be a strong reflection because of this metallic wall here. Imagine you try to put a wave coming from right to left. Obviously, there should be some strong reflection, but it should be reduced by the presence of the Coco particles. This is an idea. The other idea would be to use a parallel plate waveguide with only one height without the jump, and try to make it isotropic into D to make perfect focusing or sub-wavelength focusing, but not perfect. But for that case, I would have to use this kind of unit cell. Well, it's going to be very difficult. Very, very difficult. Well, imagine you have a Coco on this surface. For the orthogonal surface, I will have to rotate the Coco like this. Oh, sorry. Can I undo? Yes. Oh, it's very difficult to understand the figure, no?
Yeah, it's fine, it's fine.
What I mean is that we have to rotate 90 degrees one of the Cocos. If not, otherwise, the electric dipole will be double of the magnetic dipole. In this direction, it will work, I think, because imagine you have a vertical polarization. So the electric field can excite one of the Coco, but not the other. Magnetic field on the horizontal plane can excite one of them, depending on the polarization. Or maybe both of them at the same time because of some oblique impedance. But the electric dipole will be excited only once with the vertical direction. You have to imagine the parallel plate waveguides also, so the electric field is vertical. Only this Coco is going to be excited by the electric field. And magnetic field can excite any of them with the same intensity of the electric and magnetic dipole. If you try to put the Cocos in the same orientation, but just orthogonal one to another, it is a problem because you will be exciting twice the electric dipole. And then you lose the equality of the intensity of the electric dipole and magnetic dipole. So, well, there are two ideas with the parallel plate waveguides. Try to improve the transmission through the jump, or try to get sub-wavelength focusing with this unit cell.
Okay, thank you. So, dear colleagues, do you have any other questions to our speaker? So, if not, I'd like to thank our speaker again.